The Washer Method by
Taylor
and Jordan. The Washer method is used to determine volume of an object revolved around a certain line. This picture here is a representative rectangle shown to see how the Washer method works and is used with two main variables, big R and little r. Big R is the distance from your axis of revolution to the very top of your rectangle, whereas little r is the distance from your axis of revolution to the very bottom of your rectangle. Now, two very important key points to using the Washer method is that your rectangle must be perpendicular to your axis of revolution, and your second important point is that your rectangle cannot be attached to your axis of revolution. If it's attached to the axis of revolution, that's when you would look to use a different method like the disk method.
When your representative rectangle is perpendicular to a horizontal line like the x-axis, you would use the formula of pi times the integral from a to b of big R of x squared minus little r of x squared dx. The formula when the rectangle is perpendicular to a vertical line like the y-axis is very much the same as the horizontal formula. The only thing different is now it is in terms of y instead of x. Therefore, the formula is pi times the integral from a to b of r of y, of big R of y squared minus little r of y squared dy.
For example 1, we're going to be using the two curves y equals the square root of x and y equals x squared. Now we're looking for the volume that is between these two cross sections revolved around the x-axis. Shown is a graph where these two curves are drawn, and in order to determine the limits of integration that you'll need later in the problem, which one of them is the origin, where those curves intersect is going to be what your limits of integration are, which is so the curves intersect at the origin and they also intersect at 1 as shown on the graph. Now, we've also drawn a representative rectangle within these two curves, so you're able to determine your big R and your little r. So your big R is the distance from the x-axis to the point where the rectangle touches the curve y equals the square root of x, and your little r is the distance from the x-axis to the point where your rectangle touches the curve y equals x squared. So with that being said, r is equal to the square root of x and little r is equal to x squared. Now we're going to start working with our same equation that Taylor pointed out earlier, which is the volume equals pi times the integral from a to b of big R of x squared minus little r of x squared dx. So when you're going to plug this in, you're going to have pi times the integral from 0 to 1, like we talked about earlier, of the square root of x squared minus x squared squared dx. So you can simplify that down to make it a little bit easier to work with. So then you're going to be left with pi times the integral from 0 to 1 of x minus x to the fourth dx. So now you have to integrate. So you're going to be, so when you integrate your x and your x to the fourth, you're going to get as a final answer x squared over 2 minus x to the fifth over 5. So then you're going to have to plug in your upper and lower limits. So the process of that is shown here, where you multiply pi times your upper limit, which is 1, that you plug in for x. So it's going to be 1 squared over 2 minus 1 to the fifth over 5. And then your lower limit's going to be 0, which we are going to show for the process of the video and for the process of learning, but it's going to end up equaling 0 because the lower limit is 0. When you finally work that out, you're going to get to a final answer of pi times 3 over 10 minus 0, which will then give you the answer 3 pi over 10 as your final answer to the problem.
Example 2 is a calculator problem. We will be finding the volume of the graphs y equals natural log of x and y equals x minus 2 revolved around the line y equals negative 3. Shown is a graph representing these lines. So, in order to find the points of intersections needed for your limits of integration, we will plug it into the calculator. You set the natural log of x and x minus 2 equal to each other, and this gives you the x values of 0.159 and 3.146. In order to find the y values, just for the sake of the graph, you just plug it into one of your equations to determine them. So once you have your limits of integration, you can determine which one is big R and little r. Shown is a representative rectangle. Big R, as you can see, is the natural log of x, and little r is x minus 2. We will still use the equation for the horizontal line since your rectangle is perpendicular to the horizontal line y equals -3. Therefore, you'll use the equation pi times the integration from a to b of big R of x squared minus little r of x squared dx. Plugging in your points, you will get the equation of pi times the integral of 0.159 to 3.4146, which was given from your integrals that we determined before. Plug in your big R of natural log of x, but you have to add 3 due to the fact that your axis of revolution is not the x-axis. So when you have to add 3 in order to get your thing. And same with little r. So your final equation is pi times the integral from 0.59 to 3.146 of the natural log of x plus 3 squared minus x minus 2 plus 3 squared dx. So then you'll just plug into your calculator due to the fact that this is a calculator problem and you can't integrate this by hand. So when you plug into the calculator, you plug in your integral that you found and you will get the answer of 34.199.